All right, so we're inside it. So let's say we take a random sample, right? So let's say we have a random, that word there's random. Let's see if I could write neat today. So if the random sample, if the random sample of size n is obtained, right? Then you want to take a look at a few unbiased estimates, right? These are point estimates. So the first thing, the best unbiased, right, estimate, right? Unbiased basically means fair, right? Of mu. Remember, mu is the population parameter, right? This here is called your population mean. Right, so the best estimate for the population mean, and we write it like this, mu with a little hat on top, right? Mu with a little hat on top is equal to x, we know already, x bar is the sum of x all over n. So if they ask it to obtain that point estimate, that's what you're doing. All right, that's the best unbiased estimate for mu, right? Let's say you want to get it for variance now. Hold on. Suppose you want to get the best unbiased estimate of sigma squared, right? You know what sigma squared is, right? That is your population variance, right? There are a few ways you could do it. One way is this: population variance is equal to n over n minus 1 multiply, because remember we gain values from a sample, right? So it's n over n minus 1 by s squared, right? What is s squared? This s squared here is your sample variance. So from the sample, that's the variance there, right? That's one version, or a next version, right? I have a few versions, right? A next version that I might be able to use is 1 over n minus 1 by summation of x squared minus the sum of x all squared all over n. Right, that's one of the versions that I could use there. Right, so the first version, you'll use it if you have sample variance. Second version is if you just have sum of x squared and the mean and thing. Okay, that's the first two, and there's one more. This one will be kind of new. It's called the best right? Is the best unbiased right estimate of P, right? This one will be a little bit new. This is the proportion, kind of like probability, is the proportion of success in the population. So it's kind of the same way you would find probability in a way, right? So it's basically the proportion in the sample. right? This is proportion. Did I spell that right? Should I spell that wrong? Right, proportion of success in the sample. Okay, those are your point estimates. At any particular point in time, they want you to get that particular estimate. That's what you're doing. All right, copy that down. Let's try a few examples. Anybody writing there? Somebody writes in there. All right. So before we look at the interval estimates, let's just do a couple calculations. And it's real simple over here, right? It's fairly simple. I just want to give you a few values and you will find a point estimate for each one from them. Right? Quick example, right? Right, so I just given you some values here. All I want you to do is find the unbiased estimate for mean and variance. All right, so I'll take a sample here, a sample of 7 volumes, right? So let's say that is 240.8, 237.8, 236.7, 236.6, 234.2, 1, 2, 3. Actually, let's just use 5 values. That'll be easier, right? 240.8, 237.8, 236.7, 236.6, 234.2, right? All I want are the unbiased estimates for mean and variance, right? Because you estimate that you put a little hat on top. Right, just want to get method to answer. Right, remember you're really finding x bar, which is the sum of x on n, right? So you're adding up all the values, 240.8 plus 237.8. all over 5. How much you got? As you mean, allocating wrong verb. Right? Celine have 237.22. Right? Remember, it's in mean, right? So all your values like 200 and something here. Yeah, right. Check it back and make sure now. Right? And then you have to find it's only 5 values, right? So you have to find the unbiased estimate for variance now, right? So in this case, it's 1 over n minus 1, right? By the summation of x squared, right? Try that for me now, please. So you have to square all the x and sum it up, right? Then you have to sum up n and thing, right? Try that, please. You just give me I just want to get a little help with like what is sum of x squared and thing. So it's 1 over 5 minus 1. Tell me what you get for sum of x squared. Two eight one. Oh crap, it's going. 281,389.57. Right? What is sum of x squared? What is sum of x? Well, what you got for the sum of x? What was the sum of x before? 2, 4, 6, 8, 10. Jude, you put the comma in the wrong place, boy. 1186, 1186.1. Right? And then when you square it, you work it out. What you got for the whole thing? Rajiv got 5.731. Sorry, 2. Anybody else got that? Yeah. Okay, so that's basically how you find the point estimates, right? You'll need to be able to do that because now we're going to take a look at the confidence intervals, right? Or call the interval estimates. Any questions on those values there? Any questions on those values? Saskia, Grant, Dexter? Everybody okay with this? Oh, I'll give you a minute or two. Check it and tell me if you're not getting it, right? Dexter, you got these values? Saskia, get it now? You got them now? You not getting means out? Oh, you're getting mean? Okay. But let's check back your sum of x squared, right? Remember, you're squaring this, you're squaring this, you're squaring this, and you're adding it up, right? Try one more time, but just make sure you get those values. Got it? Okay, nice. All right, nice. So we have a little idea how to manipulate these values, right? Now we're going to take a look at the confidence interval. All right. So I'm gonna just give you I'll paint a little picture of what a confidence interval is, right? Let's say we have 0 to 100, right? We're not too sure what the mean is, right? But we guaranteed that the mean is somewhere between 0 and 100, right? We don't know where it is, but we are 100% sure, right, that that mean lies between 0 and 100, right? So if you wanted to be 100% sure where the mean is, you would take the lowest value 0 and the largest value 100, right? One of the examples I remember, one of my lecturers giving my example of what the confidence interval is like if you had a key in your pocket, right? And you left home and you was going to class in UE, right? But when you left home, right? When you left home, you're sure you had your key, right? You jump in your car, you drive up the road. When you reach Gasparilla now, around Gasparilla there, you recognize those shops. The key one, right? What that means now is between home and Gasparilla, you lost the key. So you're 100% sure that, you're not getting too technical, but you're 100% sure between home and Gasparilla that I lost the key. You're 100% sure. If you want to narrow it down slightly and say, okay, well, here's what I want to be 95% sure, then you could probably say, okay, let's go outside the gate, 95%. Let's say outside the gate represents 5, and then okay, now let's make it a little closer, 2, right? And then before Gasparilla is what, Brian Lara Stadium there, right? Let's say between home and between right outside the gate and Brian Lara Stadium is 297, right? It means that between there, you're 95% sure that you lost a key, right? And the key represents the mean that you're trying to find. So you're confident that between those 2 points, you have a confidence interval, or you have your mean, or you have your key in this case, right? If you want to be 80% sure, then we could probably go a little bit closer. I just want to make up things now. Let's say 10 to about 90, right? Wherever those positions are, if that is to Aruba, back to wherever you're further up the road from where you're living, right? But as a concept of what confidence interval is, you are 80% sure that between those 2 points, you will find a confidence interval. Okay? Sorry, you'll find your mean, right? So that represents a confidence interval, the interval in which you will find your mean. Well, okay with that concept? You'll follow what the interval represents, right? Intervals are the region in between, right, where you expect to find your mean. And there are different levels or different percentages that you could be sure it's there. You could be 95% sure, you could be 90% sure, and so on. Do you all understand the concept of confidence interval? Message yes or no? No? Right? So that's the confidence interval. Now we need to get values, right? So the way to represent it statistically is this: the probability of obtaining mu, which is your population mean, right, between two values is some percentage, right? A very popular percentage is 95%, or a very probability is 0.95, right? This percentage is 95%. Most popular, right? Three of the most popular is 95, 99, and sometimes 90. Right? Three, it have different ones, 94 and thing as well, right? But that's giving you an idea how to find it. All right? Good. So how are we going to get those intervals A and B? Well, to get those intervals, remember, we learned about different distributions, right? So number one, we need to determine, this is the first thing that we need, right? To determine if distribution is normal or not. Second thing that we need to do after we determine the distribution, right? We need to determine if do we have the variance, right? So do we have sigma squared? If we do have sigma squared, then we're going to have to estimate it. And the third thing that we need to know is we need to know if the sample size is large, right? Sample size, is it large or is it small, right? If it's large, then central limit theorem will fall in. If it's small, then we'll have to introduce a new fella called t-distributions. All right? So those are the things that you need to know. If you're writing, write the things in red now. Write the things in red. We're going to develop one now. Right? I'm going to show you where the formula came from. Honestly, you don't really have to memorize where the formula came from. But once you understand one version of the formula, it don't matter what conditions you change, you'll be able to figure it out, right? Anybody writing? I just kind of want to show you where it came from, right? As I said, you don't really have to know this. What you have to know is the actual formula and how to use it, right? Anybody writing? Somebody writing? Okay, let's go. So let's say I wanted to create a confidence interval, right, called CI, right? Confidence interval for mu, right? You want to get confidence interval for mu, right? So here's what we're giving you. I am going to give you, hold on. I am going to tell you, number one, remember we have to know your distribution. So I am going to tell you is from a normal distribution, right? So it's a normal population. So the values that we get is from a normal population. The second thing I'm going to tell you is that we know, so it's a known sigma squared. So we do have to work out sigma squared, right? They give us it. And then third thing, we're using any sample size. It don't matter if it's big or small. It comes from a normal, right? So using any sample size. It don't really matter what sample size you use it. Okay, right. So we would like to develop. So we would like a 95%. Sometimes I'll write confidence interval like this, right? CI. We want a 95% confidence interval. Okay. Right, so we want that 95% confidence interval, right? So what do we know? We know that X comes from a normal population with mean mu, variance, sigma squared, right? But then remember, we're dealing with the sample distributions of mean, right? So X bar is really a normal with what? Mean mu and what's the variance? What's the variance if it came from a sample distribution of means? Anybody remember? Right, very good, Grant. Grant, imagine Grant answer. Very good, Grant. Very good. Sigma squared on R, on N. Right, sigma squared on N. That is that's the distribution of the mean, right? So, sorry, sample distribution of the mean. Good. So now, what do we want to get? Right? Remember, I just put another drawing here for you, right? It's a normal distribution. The mean is here. And we would like to get, see this here? We would like to get 95%, right? 95% confidence interval. So that percentage there has to be 95%. Okay? That percentage there needs to be 95%. So I need to figure out what are these values alpha and beta. Right? That's kind of what I'm trying to figure out here. What will be those values for alpha and beta? Okay? So I need the probability between alpha and the beta that will give me 0.95. But remember, this is for the standard normal. So I should have Z here, right? Right? You'll remember how to standardize. To standardize, it will be X bar minus mu all over sigma on root n. Right? That's the way it's standardized. Okay, so how do I get that value for alpha and beta? So watch here. This value here is what? That value there is 95 or 0.95, right? Let's be more specific, 0.95. So if that value there is 0.95, if this value is 0.95, and this whole thing is symmetric, anybody could tell me what here will be? And here will be? What will those values be? If the middle is 0.95, when I add up the two green parts, I'm supposed to get what? Right, very good, very well, yeah. When you add up the two green parts, you will get 0.05. So it means that this part here is 0.025 after divided by 2. And this next green part here is 0.025. So how do I get that alpha and beta value now? Well, if you remember what we did earlier, to get that alpha value and that beta value, right? What we have to do is we're going to have to go back to our table, and we're going to have to, and we're going to have to read off this value here, right? We're going to have to read off this value here, but you can't read off a 0.95, right? What we'll do is this entire thing here, this entire value is for 0.975. So you have to figure out phi of alpha is equal to 0.975. So alpha will be phi inverse of 0.975, right? That's why you have to read the value of the table and thing. Anybody can help me there? What is phi inverse of 0.975? Very good, Grant. Grant, why are you so sharp today? And you're messaging and thing. I like that, Grant. So Grant got 1.96. Let's just do my favor now, Wally. Just look back and convince yourself, please. Look back and find phi inverse of 975 and make sure you're getting 1.96. All again it. You'll get 1.96. You'll get it there. Grant to get. Right, so alpha is 1.96. Right, actually, sorry, that's beta. Anyway, the way I label it now. Here's alpha and here's beta. So I make a mistake. I'm gonna switch back the labeling, right? So this is beta that we just found. Right, so if beta is 1.96, alpha is what? What would alpha be? If beta is 1.9, very good, Rajiv, minus 1.96. So now we can come back here and say that we have the probability between minus 1.96, positive 1.96. We're almost done, I promise you. We are almost done. Right? Remember, Z is what? X bar minus mu all over sigma on root 10. Right? Okay, good. So let us just rearrange real quick. Right, I continue from I'm right here. That's why I'm turning the page, right? Screenshot this fast now if you need it. Right, good. So last part, are we done? So basically, we had the we had we had the probability of minus 1.96 is less than x bar minus mu all over sigma on root n between 1.96 is equal to 0.95. Right, so let's just solve for mu real fast. So minus 1.96 is less than x bar minus mu all over sigma on root n. Right, carry this up here, you'll get minus 1.96 by sigma on root n is less than x bar minus mu. Right, carry across the x bar. Actually, here's what, let me just switch everything around. X bar minus mu, right? Remember, if A is less than B, then B is more than A, right? So x bar minus mu is greater than minus 1.96 sigma on root n, right? Carry across the, right? Carry across the x bar, you'll get minus x plus 1.96 sigma on root n. Right, which is the same as mu is less than x plus 1.96 sigma on root n. So mu is less than that value, okay? Mu is less than that value. So this value here is the upper limit, but that is the upper interval. You do the same thing on the next side, and you will get mu is more than x minus 1.96 sigma on root n. Sorry, not x bar. Right? So in short, if you wasn't paying attention to me, pay attention to me now. In short, the confidence interval at a 95% confidence is equal to x bar minus 1.96 sigma on root n, and the upper boundary is x bar plus 1.96 sigma on root n, right? So if I ask you to find the confidence interval, right, find the confidence interval at 95%, given that you know it's a normal and a given variance, that's what you're doing there, right? That's your formula. Oh no. Right, so make a note of the part in blue. As I said, I just went through all of this because I wanted it to have a little appreciation of where it came from. If you don't catch it and have little things to get, you could always look back at it later on. But what I want you to pay attention to is that part in blue, right? And to save you some trouble, I will give you the confidence interval also. Confidence, so you don't have to go and work it out. Confidence interval at the 90%. All that going and change is that value in the middle. 90%, it will be 1.645 sigma on root n. X bar plus 1.645 sigma on root n. So if they change it to 90%, that's the formula you're using. If they change it to, let me write one more. If they change it to what I told you all earlier, 90, 95, 99 to 99%, it becomes x bar minus 2.576 sigma on root n, x bar plus 2.576 sigma on root n. Okay, so those are the three formulas that I wanted to learn. 1, 2, 3. right? So all we have to know now is, okay, so what do we do? What do we do if it's not a normal? Well, if it's not a normal and n is large, we could use central limit theorem and say, okay, here's what. By central limit theorem, right? By central limit theorem, it still follows a normal, right? If it is normal and you don't know the variance, all we're going to have to do is to estimate the variance, right? All we have to do is just estimate the variance. And lastly, if it's normal and the population is small, which is less than 30, then we do something new, right? Right? And we don't know variance and the populations and the sample size small, something new called the t-distribution, right? Not today as well. All right, let's learn to develop now a confidence interval. Right, so I want to show you formulas, right? Let's try a small example. All right, so let's try example 1. Suppose I give you a distribution. X follows a normal distribution. So I told you it's normal, right? X follows a normal distribution with mean mu and variance 0.042, right? A random sample of 5. So let's say we take a random sample of 5, right? In a random sample of 5, the mean, which is the x bar, small x bar, the random sample was found, the mean was found to be 5.12 milligrams, right? Let's see if we could find a 95% confidence interval. Okay, we want to get that 95% confidence interval. All right, so the first thing we do is we write x bar because that's the distribution that we're using. X bar is a normal with mean mu. We still don't know mu, but the variance is now sigma squared on n, right? What is sigma squared on n? We can work it out one time. All right, let's work out that one time now. Sigma squared on n will be 0.042 all over 5. Okay, that's the sigma squared on n, right? We don't really need it right now, but I just wanted to show you, right? Now, we want to get a 95% confidence interval. So go back to the formulas that I just wrote, and you would see that is x bar minus 1.96 by sigma on root n, x bar plus 1.96 by sigma on root n, right? Right. I want to ask something, right? Some of you have paid attention while I was doing the proof, right? This sigma value I use in here, is it this value or this value? That sigma value I'm using there, is it the first or the second value? Message, please. What you all think? Do you think it's the first sigma value I'm using or the second sigma value I'm using for there? Just message one or two. You don't have to message the exact thing. Do you all think it's the first value or the second value? All right, very good. All right, keep messaging, right? And the answer is the second value. It's the second value. So this is the value that we're using for sigma, right? At no point in time did I separate this and work it out. The sigma I used in my proof was this sigma here all the time, okay? So I don't want you to come and use this value here, right? I don't want you to use that value there. All you're using is the sigma squared given initially, right? That was the sigma that I used in the proof. When I was doing the proof, this was the sigma I was using all the time. Okay, So don't use that new sigma squared on here. That just guided us to develop the formula. Okay? So the confidence interval now is X bar. X bar is 5.12 minus 1.96 by sigma. As I said, sigma is 0.042, right? Sorry, sigma is the square root of that, all over the square root of n. So all over the square root of 5, right? That's your lower boundary. Then you do it again. 5.12 plus 1.96 by the square root of 0.042 all over this 5. Okay? How much is that? Check it from now. What's the upper and the lower boundary? We'll get out, tell me what you get, right? Right, what you all got? Right, so 4.94 and 5.3, right? So we had to pay attention to what they give you, right? I gave you the variance at 0.042, right? So you had to pay attention to that. And don't forget that standard deviation is the square root of 0.042. Okay, so you had to pay attention to what they give you. Any questions here? Any questions here, Olia? Saskia, any questions? Any questions there, Olia? Are you okay with this? All right, so we're going to try one. You have to pay attention to all the important parts in the wording, right? So, by the way, for those who have time, right? What you could do is this, right? You could find the probability between 4.94 of mu and 5.3, and you should get 0.95. Right? All right, good. Let's try one now. Let me see. Let me see. Let me see what we get. Give me a second. Just trying to get to the end of this. This to the end. This. I want to give you one way. You don't have too much work to do. You know how it is. Don't want to give you no work to do, eh? I want to give you a little work, right? I'm gonna just point out some things here for you, right? You have your variance given, right? You given your variance, you given your sample size, you given your mean. Once you have those, and you're given your percentage confidence interval. Once you have those 1, 2, 3, 4 things, then you could dive into the formula, right? Remember that, yeah? I'm gonna give you one here. I don't want to be no substitute lover, right? Very still. Right, so I'll give you the other conditions for confidence interval next day, and then we take a look at hypothesis testing, and that's it for this module, right? All right, let's go again. Take off this. Pay attention to those same 4 things that I point out, right? Try that, please. Any values? So we know n is 6. You had to work out x bar, right? So you had to add up all. So here's an example where I use the point estimates. Add up all and divide it by 6. Well, I get for the mean. Ooh, Jude don't play, right? Jude is done. Like done. Jude is like done, you know. Variance is 4.5. Right? The mean, what you got there, man? You got 12.45. So you have everything you need there? Hurry up. Rajiv is a close second. Varun, ooh, something going on here. Rajiv, just check back yours there. I ain't saying you're wrong. Two of them could be wrong. Varun could be wrong. Or Jude could be wrong. But just saying. Just check back yours there, Rajiv. There's a chance. There is a chance in my pocket. Any more? Oh, I didn't mention was the width. Right, the width is just a subtractive values. That gets in 40. Any more answers? Go ahead. You have some more time. Right. Saskia, yours looking good. Barry, yours looking good. Celine, check back yours. Dexter, what you got? Dexter, how much you got? 1 point. Take a picture and some. I'm gonna see why you make a mistake. Take a pic and send it to me. So then you can take a picture of yours too. Right, so basically the formula is equal to x bar minus 1.96 sigma root n by x bar plus 1.96 sigma root n, right? So I'm using 1.96 because it's a 95%, right? Confidence interval. So that will be 12.45 minus 1.96 by the square root of 4.5 over the square root of 6. 12.45 plus 1.96 by the square root of 4.5 over the square root of 6. Right? And once you do that, and here's something that's important. So you will get 10.75, 14.15. Here's something that's very, very, very important when you're working this out. It's a check to see if you answer right or wrong, basically. What you have here, this here is your mean, right? Your mean should be between those two values. So if by some chance you work it out and you're getting a value like 4.7 and 6.3 or something, some crazy thing like that, your mean is on the outside here. It's not within the interval. So even the sample mean should be inside it. Okay? It should not be bigger than 12 point. Both shouldn't be bigger than 12.5 or both shouldn't be smaller than 12.45. Are you okay with that? Yeah, Grant? You okay with that? Okay, so next day we'll do confidence intervals, but we'll do them where we don't know the distribution, sample size big. Then we know the distribution, sample size small, and we don't know the variance. Right? So we'll do all of those. And then we finish up that, right? Oh yeah, Celine, I see you there. What you did wrong there, Celine? Oh, you fix it now. Oh, you can't be sending the fixed thing for me. What kind of smart thing you're trying after I write it? All right, any of your classmates here, Celine? Or it's just you? Just you. You know, time, huh? All right, so that, yeah, that's it there. Right, next week we'll continue with we will continue from right here. So it might be nice if we could go over this before we start.